How many NYU people do we have in the house? How many friends of NYU do we have in the house? Great, thank you so much. Welcome. We wanted to so my name is David Cantor, this is Sonali McDermott. We're both professors in environmental studies at NYU. We're just going to do a brief posting before we bring all the amazing scientists up. And we just want to, well, first make sure that we're as loud as the stage, and secondly just point out that nothing says science like a shower curtain duct taped to a tent side as a projector screen. Right. We wanted to give you just a brief overview for why we're here. Why is NYU? We were the first official university partner of the March for Science. We're really proud of that. And it takes a lot to get some scientists, particularly tens of thousands of scientists, out of the lab, out of the office here on the National Mall to march and celebrate science. And we're here, NYU is here, because we want to celebrate the importance of science. The science is a common good, and the importance of evidence-based decision-making and the contribution that science makes to that. We also want to celebrate the importance that science does in promoting diversity and underrepresented minorities, in bringing them into STEM subjects and promoting the really important work. And we also want to promote the importance of public-funded research, the importance that government has in making sure, in doing the kind of science that, as much science comes from private sources, and that's great, the role of the government and public-funded sources of science is really important, and that's one of the reasons that we're here today. Okay, so I'm going to run the mic over to Sonali, who's going to explain how we're going to run this crazy 50-minute session. All right, thank you so much for being here.
All right, so everybody knows science is generally slow. Today we are turning that on its head, and we are doing speed science. Anyone done speed dating before? This is speed science. We have brought together an incredibly diverse group of researchers across NYU, which rarely happens at NYU, and we want to give you a flavor of what research is like in the hallowed halls of the university today. We're doing modern work for the public good, for the common good, and so each of our scientists is going to get 5 minutes to tell you why what they do is important. I'm going to shout out a 2-minute warning. You are going to cheer them as they get the message across, and then we're going to have a good 10 to 12 minutes for a full Q&A session. Sound good? Yeah. First up, we've got Cassie Thiel.
Hello, everyone. I'm just going to squish down here. Too tall. You're going to do this? Okay. How many of you have ever gone to a store and tried to buy something and it said it was green? Have you ever wondered if it was actually green? Yes! All right, so let's talk about life cycle assessment. I'm going to go through an example. Everyone loves chocolate, right? Yes. Most people do. Okay. What goes into making a chocolate bar? Chocolate. That's it. Sugar. Milk. Those are all great. Maybe eggs, depends on where you are. So this particular one has chocolate, peanuts, peanut butter, pretzels. You get the idea. Some good sweets, right? So if we want to think about this from a systems perspective, we have to start going upstream. Where do those things come from? This is what happens in a chocolate making factory, by the way. You have your raw ingredients, milk, sugar, chocolate. Those all come from somewhere. Where do those come from? Where does sugar come from? Sugar cane usually. What about milk? Cows. That's awesome, you know that. I'm from Wisconsin originally, and I love cows. Chocolate comes from cocoa. It's a tree. So we map this all out, and this is maybe a rough estimate of what that might look like. We go upstream, and we could keep going forever, but that's an idea there. Something comes out of this chocolate process. What comes out of making or eating chocolate? I hear some laughter over here. Cholesterol, that's good. Methane. Caloric energy. Nitrate. There's something else. Waste. Very good. Garbage, human waste, and waste. Wait, energy. You get some energy out of this chocolate bar. So we have to also think about the downstream side of our chocolate bar. So if this is our factory, right, we have some packaging. It's transported, it's used, and it ends up either in a landfill, hopefully in a wastewater treatment system, and you get some energy to go about your day. And so that is kind of the life cycle of chocolate. And if we want to know how green this is, we have to start thinking about what goes into each part of the system and what comes out of each part of the system, because every stage has waste, every stage has emissions. And so what life cycle assessment does, this is an official tool that's regulated by the International Organization for Standardization. And so it has a few steps. I'm going to talk about 2 and 3 here really quick. So we have at each stage some inventory, right? There's emissions coming out of everything. If it's CO2, methane, if we're talking about global warming. In our step 3, we add those all together into respective columns. And to add them, we might have to multiply them. So in the case of methane, it's about 23 times more potent than carbon dioxide. And so we get that all into units of kilograms of carbon dioxide so that we can report that to you as a carbon footprint. And that's how we look at life cycle assessment of things like chocolate or whatever you're going to buy that's green. We can say this is greener than other products because this is the emissions and it's lower than other products. So that is life cycle assessment. I think I've gone through this really fast. Life cycle assessment to look at medicine. So you may have heard that medicine's a little bit wasteful in the US, and so we're trying to find ways at NYU to fix this problem. And so that's how I use life cycle assessment. I will hand it over to the next person and we'll keep cruising.
Give it up for Kathy Field. Now let's welcome, I think it's Kent, right? Yeah. Kent Kirschenbaum and Dirk Trauner are going to talk about a taste of chemical neuroscience.
Thank you very much. I'm Kent Kirschenbaum, and this over here is Dirk Trauner. Let me just say how proud I am to be part of the NYU community of scientists, and how appreciative I am of my colleagues who assist me in doing research in developing drugs for prostate cancer and other diseases. I'm so delighted to be here, and I've got to tell you, as a chemist, there's one thing that drives me crazy, and that is when somebody tells me that they don't want chemicals in their food. My mother-in-law gives me this grief all the time. She tells me, you're a scientist, stay out of the kitchen. I don't want chemicals in my food. And I'm here to tell you that all of our foods are composed of chemicals. All of our flavors are of chemical origin. And everything that we perceive, all of our senses rely on chemical phenomenon. And so Dirk and I are going to give you a little snippet, a little taste, if you will, of what happens at the chemical level when we taste something. And so what I'd like to do is find a couple of volunteers who are willing to undergo a variation in their taste process. So I have one volunteer over here, and I want you to take this pill. I promise you it will do you nothing but good, and just swish that around on your tongue. And one more volunteer here. One more volunteer here. Okay, so let me tell you what it is that you've agreed to do. A little bit late, I know, but this is a pill that's composed of the miracle berry. This is a tropical fruit that actually has a protein in it that's capable of transforming our taste perception. So let me just give you a little flavor for what goes on. Here is a protein here on the left. This is actually a protein that resides in our taste buds, and when molecules interact with this protein right here, it triggers a taste response. And in particular, this protein is responsible for our sweet perception. So when you consume this protein in this berry that I've just given you, there is a binding event between the chemical constituents of that fruit and that taste receptor. Now, what happens initially is absolutely nothing until there is a change in the acid level in your mouth, and at that point, we're going to find out what happens. But first, we're going to allow that pill a little bit of time to infuse into your taste buds. And in the meantime, I'm going to turn it over to my colleague, Dirk Trauner, who's going to tell you about what he's doing with the taste response.
In 2 minutes.
Thank you, Ken. 2 minutes, I'll be fast. So taste and food is not only associated with sour and bitter and umami, savory, and things like this. but it's also associated with hot and cold, and touch, and yes, with pain. And that's what we're working on. We're actually working on a receptor that is responsible both for hotness, the painful feeling of hotness, and hotness as in red hot chili pepper hotness. It's called the capsaicin receptor. It's a so-called tryptophan, it's a protein. And this protein opens at 42 degrees Celsius and it stimulates neurons to tell you there's a hot plate, withdraw your finger, it's hot, it's noxious, it's bad for you. But this protein is also sensitive towards a small molecule called capsaicin, which is the major ingredient of red hot chili pepper. So for a chemist, it's absolutely fascinating that red hot chili pepper hot and hot plate hot is the same thing on a molecular level, on a physiological level. Huh? So these things can feel temperature, they can feel chemicals, well, and we are engineers and chemists, we thought let's make them feel light. So we actually made capsaicin into a molecule that can be switched with light. This is a so-called azobenzene, and it changes its shape when you radiate it with light. And with this we can actually change the punginess of this compound, the hotness of this compound. And with this we have created a chemical, a food ingredient that responds to light, and have created the most important field of photogastronomy. So stay tuned for further insights into photogastronomy.
Okay, and now time for the taste test, and we need a control. Somebody who is going to taste the lemon. Anybody willing to just taste the lemon?
I'll taste it. Here we go.
And now the people who've consumed the miracle berry. So as you're doing this, you're acidifying your taste buds, and you're undergoing a protein conformational change. Taste that. Tell me what it tastes like. Does it taste sour? It tastes sweet. How about your lemon?
Sour.
It's sour. Transformation. Let's end this up with this message. You are what you eat. You eat chemicals. You are chemicals. Be good to your body. Think about what chemicals you put in there, and be sweet to others.
Thank you. Okay, now for something slightly less sweet. Carol Reese. Carol is very sweet.
Thank you very much, and thank you all for coming. I'm going to tell you about some infections that I know that you've heard about and you may be worried about. So I'm going to tell you some aspects of this, and I know that the time is limited, and if you want to talk about this more after the session, I'll be happy to, because each of these could be an hour-longer lecture. So Ebola you've heard about, but you've heard about it largely in Africa, and you've heard about it being very, very lethal. Now, this is the case when you have 200 patients in a ward, a little bit larger than this tent, with just a handful of doctors around. When you have one patient and a team of 100 doctors taking care of them, it's a different situation. Now, Ebola comes out of animals, including the non-human primates and the bats, and sometimes enters the human population, either through eating or farming, or trying to harvest the non-human primates, and then people spread it among each other. The signs are that about half may die, but it's much better if you seek treatment early. And this is what the virus looks like, and this is how the people who take care of the patients have to dress to protect them from getting exposed, because all biologic fluids are potentially a source of infection. Zika is not spread from non-human primates directly, but it is indirectly by the mosquitoes. And the Aedes mosquitoes are found in tropical areas, and they're working their way up here with the climate change. Now, Aedes mosquitoes carry many other infections, and we actually wouldn't care at all about Zika, because generally only 20% of people who get bitten by a mosquito infected with Zika experience any symptoms at all, and it's mostly a cold with some rash. But if you happen to be a pregnant woman who is exposed early in gestation, then you can have a profound effect on the development of the brain. because the virus can infect neurons and can prevent them from growing and thus have long-term effects on the ability of those individuals. It may even be incompatible with life if they're infected very early in gestation. The earlier, the greatest effect. So what we have to do is we have to prevent exposure to mosquitoes. And there are lots of ways to do that. We don't have time to talk about that now, but basically avoid mosquitoes, and then you won't have to deal with Zika. The last is the flu. Now, this is how flu is spread. It is spread by people sneezing and coughing. And you're not even aware about how far the virus goes, because actually all you can see are really big water droplets here. It's the water droplets that are over here from that person that are actually spreading the infection. And so if someone had an elevator before you, those droplets are still in the air, and then you can inhale them. Now, a lot of people say they have the flu 3 times a year, but really you don't get the flu 3 times a year. At best, you get it once every 10 years or so, because that's when the virus has a major change. And you can see here that there have been sequential changes over time of the capsid proteins, the hemagglutinin, and the neuraminidase. And it's when those proteins have a major change that everybody gets sick. It's called a pandemic. Now, with flu, in New York City, every year with the seasonal epidemics, 1,000 people die. But you don't need to die from flu. We have a vaccine, and also we've got antibiotics for the secondary bacterial infections. But I recommend the vaccine for flu. We have a vaccine for Ebola, which was just discovered because we have wonderful science that was funded by the NIH. And we have science which has developed diagnostics and new therapeutics for all these infections. And so it's by supporting research that we will be able to deal with these, we'll be able to detect and treat them. Thank you.
Give it up for Carol Justice Rice. Next up, we have a representative from the School of Nursing at NYU, Jin Ju.
Hi everyone, who's excited to be here today on a rainy day. I'm one of the excited people. My name is Jin Jun. I'm a nurse and I'm a PhD student. By the way, I'm fighting with that music, so please feel free to dance if you want to. I'm not a professor yet, so I have my notes. So I want to talk briefly about early childhood caries, also known as cavity. And it used to be called baby bottom mouth for those people that raised children back in the days. So did you guys know that it's an infectious and chronic disease that's very common, 5 times more common than childhood asthma. And asthma, we all know that it's extremely common with younger children. And this early childhood caries actually causes a lot of problems with children. It leads to chronic pain, infection, and sometimes they lose the function of chewing. And this is especially a problem with those living in poverty. And more than half of those children living in lower income families, even adolescents, have cavities that affect them on a daily basis. And these cavities limit children's ability to eat, sleep, and play, and most importantly, to learn. They can't always tell you when they have pain, so they will exhibit behavioral signs. So they come up as irritable, and they are not doing well at school, they don't want to go to school, they just want to sleep all day, they're acting out, all those things. But the biggest problem of all this is that more than 108 million people in this country do not have dental coverage. And even when they do have dental insurance, they can't find providers that take their insurance. So why does this matter for nurses? So who these little babies that when they get these baby teeth and their mothers, who do they come to see? Their primary care providers, including a lot of nurses and nurse practitioners. And it's actually the nurses and nurse practitioners, I feel like I don't have to scream anymore. They are the ones that are actually looking at the baby teeth and doing the information and the mother-baby teaching. And what's really important is this. that the germs that's causing cavities can transmit it from the mom or the caregiver to the babies through behaviors such as saliva sharing behaviors. So for those that raise children, remember that when they drop their pacifiers, which is every 5 million seconds, you pick them up and you clean it with your mouth and give it back to the babies. And those behaviors can transmit the bacteria that leading to cavities. And what's really important, one of the things that we teach the moms is reduce the sugary drinks. And that's a problem not just because sugar is bad that we all talk about, but because it creates the acidic environment for the teeth. So the baby's teeth never get to the safe zone in the green when they're always sipping those juice or high glucose or the sugar content. So we teach them to give water in between the meals, and even the little baby teeth, we recommend that brushing their teeth twice a day using fluoride-based toothpaste. So I talk about all this because we tend to think about nurses as those people at the hospitals giving shots. So this is just a slide about the high risk for the poor families, but the nurses, we are important because we are everywhere, not just the hospitals. We are at your schools, your communities, your churches, and your doctor's offices, and even your homes. And what we do is actually based on science, and we use these science and evidence every single day in every single interaction we make. And we nurses continue to seek to gain more scientific knowledge, and so that we could improve the health of our children, our communities, and for all of us. Therefore, we need our government to continue with their funding. They actually cut the funding for nursing education starting next year. So we need those fundings to continue to build our nursing scientific knowledge and to create that critical nursing workforce that we depend so much on. So I thank you for this opportunity to represent nurses and nurses. Thank you so much.
Thank you so much, Jen. And now to switch it up a little bit, we have Ed Gerber from the Atmospheres and Oceans Division of Courant Math Institute.
So I'm going to try to teach you about 500 million years of Earth's history in 5 minutes. So this is a temperature record of paleoclimate. Paleoclimate is the study of past climates. Climates when there was no one around to measure it with a thermometer. But we can still estimate the temperature by looking at proxy records. For example, like ice cores, these blue records here. What we've done here is we've actually stitched records going back 500 million years. And it's a funny kind of log scale here, where this is hundreds of millions of years. And then it gets kind of shorter and shorter until we get thousands of years up to here. So if you look back a few hundred million years ago, as like everyone knows, when the dinosaurs were around, it was much nicer, like tropical country. The whole world was a tropical place. If you go back a little farther, it was actually an ice age back then as well. But then we go. This is the when all the dinosaurs were killed off, either asteroid or something. And then the Earth starts cooling off towards the present. So the question is, what sets the temperature of the Earth, and why does it vary so much? The main players is that we don't want energy from the sun. So either the sun could change, that's one thing, or we can actually change our color. The Earth starts reflecting more radiation. When it gets whiter, for example, like snow, it reflects that radiation and it can cool down. The other thing it can do is it can vary its greenhouse effect. This is how much of the heat you can trap in. If you have a jacket, the Earth will be a little bit warmer. So we think when you come back here, the dinosaur age, there was a lot more greenhouse gases in the world. And that's partly because you really need plate tectonics and everything to excel this. There weren't any polar continents. There's a lot more volcanism getting out the CO2. And then over the last 80 million years, though, we've been kind of eating up that CO2, putting it back into the Earth, cooling down until we got to this interesting phase where now we've got ice ages going on. So the question, I want to zoom in, especially if we're interested in the future. Let's go to the ice age period. So this is just the last part of it. Here now, all the continents are in pretty much the same place. The sun's pretty much the same. The question is, why are sometimes we sort of nice like we are today? Sometimes we have woolly mammoths all over the place. And the issue is really that it's all being set by very subtle iterations of the Earth's orbit. So that the North Stars are our North Star now, but in a few thousand years it won't be anymore. We got to tilt a little bit. And what it turns out the key thing is how much sun you get during Northern Hemisphere summer. Because that's where our continents are. If you want to build up an ice sheet, you get a nice cool summer, the snow doesn't melt away very fast. And what happens is, it happens to scientists as well, especially if you go crazy. is you get a little bit more white around the top. So you get to say, oh, it's not so bad because there's not much sun at the top. It gets a little colder, and then you get a feedback going on where, okay, now we're getting less sun's radiation, but then the ocean gets involved, and it starts sucking up the carbon dioxide. We're losing our jacket, and when the CO2 goes, then actually it gets colder, the moisture gets out, and you really build up these nice, beautiful ice ages that come around. So one question is, how do you get out of an ice age once you're stuck? Well, partly the sun shifts back a little bit, because we've shifted our orbit. But the other thing is, we think, if you're from New York, the snow gets kind of dirty after time. So if it gets dirty, it gets dusty, then it gets really dirty. And then what happens is it starts to melt. That you get actually that albedo effect goes away pretty quickly. Some other exciting things might happen, like ice instabilities in the ice sheets, in the oceans, and everything getting involved. And what you find is you get these really fast jumps right out of the ice sheet, and you kind of build it up slowly and break it out. So why is this relevant for going into the future? Well, this is where we are today, and these are our projections for the end of the century if we just use all the coal we can. And the question is that we think that it's these feedbacks that make it dangerous. And the reason I'm here today is because I have kids, and they're probably going to live to see the climate we're going to produce. And I know I really want my kids to have a good education. I want them to have a good economy, but I know that they can have a good, healthy planet as well. And it's not a choice, really. It's just a matter of getting together. Thank you.
Give it up for Ed Gerber. All right, thank you so much for sticking with it. We have 2 more talks, and then we're going to get to a Q&A with all the speakers, so start kind of, percolating the questions. Our next speaker from the NYU Stern School of Business. Do we have any Stern people in the house? All right. Alex Barash, please welcome to the stage, Alex.
Changing the pace a little bit, I'm a social scientist, all right? So I'm going to tell you about psychology. So, like you said, I'm at Stern, and I'm going to tell you about how incentives affect charitable persuasion, and I'll show you how incentives can undermine people's sincerity and affect their ability to raise donations for a charitable cause. So a little bit of background first. While incentives can be effective in many domains, a great deal of research in psychology suggests that sometimes incentives can backfire. In the domain of pro-social behavior, which is intended to help others, like blood donations, volunteering, and environmental acts, incentives can sometimes crowd out or displace intrinsic motivation, reducing effort in the very activities that the incentives were designed to motivate. Why do these perverse effects occur? Well, incentives can change the meaning of an act from a social exchange performed out of caring or communal norms to an economic exchange that's done for money or personal gain. And this can create ambiguity in people's minds about why they're doing an act and make people question the purity of their motives, which can in turn decrease charitable behavior. So we wanted to see if we could extend these results into a new domain, looking at charitable persuasion or charitable fundraising. So we recruited persuaders who were told that they'd be making a pitch on videotape for a charity or cause of their choosing. You can see some of the most commonly chosen causes there at the top. And then we randomly assigned them to one of 2 conditions. In the no incentive condition, they just made a charity pitch without any further instructions. In the incentive condition, we told them that they would be paid $1 for every dollar that they were able to raise for the cause. So they were incentivized to do a better job on the task. Then we showed these videos that they made to a separate group of target donors, and these target donors decide whether they'd like to donate. They don't know about the existence of the incentives in phase 1. So what do we find when we show those videos to that other group of donors? Well, they actually gave less money to the incentivized persuaders than they did to the non-incentivized persuaders. Again, even without knowing that the incentives existed. And interestingly, we don't find any differences in concrete aspects of the appeals. There's no differences in length or the specific content that people mention in the appeals. But what we do find is that the incentivized persuaders, they come across as less sincere or genuine. Something about the incentive impedes their ability to convey their true concern in a way that appears genuine to others. Because we think this is the incompatibility of altruism and self-interested incentives, what we did is we ran another study where we add a 3rd condition of a non-selfish matching incentive. where the reward doesn't go to the individual, the persuader, it goes to the charity or the organization. And we find that the matching incentive is more effective than the personal incentive, which suggests that in order to see these negative effects, these crowding out effects of incentives, there has to be that conflict between the altruistic act and the personal incentive, and that is where you get that negative force. So to kind of bring it back, all the important implications for social impact, obviously there are a lot of domains where incentives are used, and a lot of domains where still your good outcomes depend on perceptions of sincerity. So this is the case with charitable fundraisers, where people are soliciting donations or crafting charitable appeals. This is the case when leaders and politicians are incentivized by lobbyists, but then they need to go advocate for an important cause to Congress. This is the case with teachers who are incentivized by school principals to have good student achievement outcomes. And of course, with doctors who are incentivized sometimes by pharmaceutical companies to prescribe certain drugs to their patients. All of these are domains where incentives are commonly used, but where sincerity is very important for communicating with people, whether it's Congress, students, or with patients. And so our research really suggests that they should be aware of the negative effects, the potential negative effects of incentives. They can have this backlash effect and undermine sincerity and effectiveness with negative consequences for people's image and effectiveness. So thank you guys very much.
And finally, last but not least, we have Will Evans who's going to talk to us about scam.
So, last November, I was hosting a party, an election returns party. It was the worst party I've ever been to. And so, as the result became clear, people started leaving and various mixtures of anger, depression, and disbelief. And I turned to my friend who's in the same PhD program as me, and I said, I don't think I can do science anymore. So there I was, about halfway through my neuroscience PhD program, now thinking that this whole science thing was just a waste of time. In the face of everything that seemed to be coming down the pipeline, it seemed to me, what would be the point of studying something that only a few other scientists might really care about? But so the next few weeks were really hard for me. It seemed like there was this conflict between wanting to pursue science, but also wanting to do something useful. But then I started thinking, well, maybe there's some way that I could use science. Maybe there's some way for scientists to be really effective activists. But I didn't really know what that would look like, because although a lot of scientists want to give back to society, for the most part, we're not that politically active. So I held a meeting at NYU, and I invited the neuroscience and psychology departments to come together and think, after the election, what should scientists do? What kind of special skills do we have to offer? And so, among others, we were thinking, well, we're pretty good at understanding complicated stuff. Just looking at a big body of literature and kind of understanding a topic fairly quickly. And then we think, well, some of us are pretty good at helping non-scientists understand complicated stuff too. And we thought that these were some pretty important skills that we could maybe donate to organizations that were doing like really good social justice work. So we formed a group called SCAN, or the Scientist Action and Advocacy Network, and we started meeting regularly and contacting organizations to say, you know, we're scientists, what can we do? And the group that we've been collaborating with most is Raise the Age New York. So a little bit of background. When we started working with them, New York and North Carolina were the only two states in the whole country that automatically try all 16 and 17-year-olds as adults, subjecting them to the full criminal justice system, from courts to prisons. So we reached out to them, and they've been trying to promote legislation to raise the age of criminal responsibility from 16 to 18. So we reached out to them and we said, hey, we're a bunch of developmental psychologists and neuroscientists, and we know a thing or two about adolescent development. What can we do? And they said, oh, that's great. We go out to lawmakers and the public, and we try to make the case that adolescents really are different than adults and need a different kind of criminal justice system. But it would be more powerful if we could really have the science behind what we're saying. So can you put that together? And so we got to work. We started meeting every other week and assigning different papers, like the relevant papers in the literature to this topic. And we started putting together a report. We made plots, like this one, which shows that as you age, your cognitive ability reaches like near adult levels by about 16 to 17. So this is your ability to do working memory tasks and stuff like that. But your emotional maturity, so this is your impulsivity, your resistance to peers, your risk-taking, remains at childlike levels. until past adolescence. So there's a lot of different scientific evidence that says that the adolescent brain really is different than the adult brain. So we put together this report, and they started using it in their communications and their social media. And we also went out there. We talked to the New York City Council about this, and we also spoke at a press conference in Long Island to put pressure on a state senator there who was a critical vote. And then about 2 weeks ago, the bill actually passed the legislature and was signed into law. We can't take all the credit for this because this was a movement that had been happening for years before we joined in, but it was still like incredibly exciting. And we've got a few other promising projects going, like one with a tenants' rights organization in New York City, and another group that's trying to eliminate or change the use of solitary confinement in New York State. And we're doing sort of similar things for them. So this has been really fun and interesting and rewarding, and I just want to leave you with a few take-home lessons if you want to be more politically active, whether you're a scientist or not. So the first lesson is that you're going to have to organize with other people, and you should organize with people who are physically close to you. One reason that we've been able to pull the report together really quickly is that we have really strong attendance because we just meet in the same building where we all already are. So think about organizing with like-minded people who you work with, who you go to school with in your neighborhood or your religious institution, whatever. So that's lesson number one. And the lesson number two is that you have more power than you think. So do what you're good at. Are you good at teaching? Are you good at writing? Do you have business skills that you could offer pro bono? Are you good at tweeting? Social media is like a legit professional skill that a lot of organizations could use. So those are the lessons I want to leave you with. We're SCAN, the Scientist Action Advocacy Network, and if you're a scientist, we're definitely interested in talking to you and sharing what we've learned and spreading this model of scientific engagement with the public and policy. So we'd love to talk to you. You can get in touch with us through our website or through our social media. And that's what I've got. Thanks.
Give it up for Will Adler, and give it up for all the speakers that we've had today. I guarantee you this is the only time you will see about 8 departments in 35 minutes from a university. Not trying to recruit you. So what we're going to do right now is a Q&A, okay? Well, before I do that, I do want to mention that NYU, the DC campus, is hosting a post-March debrief. What we're going to talk about, it's going to be, there's going to be a panel, but it's also going to be a lot of audience participation where we talk about our impressions of the day, what we can do moving forward, what institutions like NYU can do moving forward. It's at the DC campus. It's open to everyone. There's going to be free pizza. It's 1307 L Street Northwest. If you're interested, it'll start at 4:30. So hope to see you there. And now we're going to do a Q&A. So if we can invite all the speakers back to the stage. If you can flank the screen so you don't get blinded. And then what we're going to do is take questions from the crowd. So if anyone just wants to raise your hand, and then we'll pass the mic. There's one right just behind you.
Hi, this is a question for the psychologist.
Speak a bit louder.
This is a question for the psychologist. So I have a friend who's a professional fundraiser, works with large donor acquisition, and worked in that profession for 20 years. And I'm curious at whether you've done any studies with, the example you were giving seemed to be something more like a test case, but this is a person who's professionally engaged in an area in which he feels passionate. Does that affect their judgment?
Yeah, it's a good question. We do have some field studies that get out into the real world. I can tell you more about them later. So my recommendation to people on the ground doing this stuff is to remember that incentives have different forces. So as a psychologist, I try to isolate one little piece, and I'm looking at sincerity in my research here. But incentives also are effective at bringing in people who are going to be more motivated. So there's self-selection effects, and that's a very powerful force. And they also are good at motivating people who are not already intrinsically motivated. So they have these other pieces, and when I show this work, I like to be careful to not overclaim. But in terms of incentivizing employees, I would say using things like gifts and verbal rewards. There's a lot of incentives that are less harmful than monetary incentives, and that could be a good way to bring incentivizing forces into play without crowding out sincerity or effectiveness.
So shout out your question.
The virus lady. Viruses have different strains, and that the flu shots and
So the question is, do viruses have different strains that morph every year, and so there's some change every year?
Okay, so that's a very complicated question because there's so many viruses. Influenza has 3 different strains that infect people each year, and many more strains that infect animals. For Ebola, there are 4 strains, but one is mostly active in Africa. For Zika, there's an African strain, and there's the strain that was in Asia that came probably with tourists from Asia to South America and then spread through South America. But many viruses have different strains, and prior exposure to one can influence susceptibility to another. For instance, dengue has 4 different strains, but with dengue, although you can be immune to the one you had the first time, it puts you at much greater risk to severe infection and disease with the second strain you get exposed to. You get dengue hemorrhagic fever instead of just dengue, and it can be lethal.
So vaccines have to keep up with the different...
Vaccines are life-saving. They prevent disease, and they can prevent severe complications and prevent death.
Yeah. Hi. I have a question for the first speaker. At the end of your talk, you talked about, just briefly, medical waste and how little of that is recycled. Of course, much medical waste is not allowed to be recycled because it's considered biohazard and has to be incinerated. But what do you suggest we should do, or policies, to increase amount of medical recycling?
So thank you for that question. That's a great question. Yeah, medical waste is difficult to recycle in some circumstances. But if you think about hospitals as a whole, there's a lot of areas where you can recycle. Administrative places, right, where there's no patient contact, even there's not as much recycling as there could be. So there's lots of opportunities without addressing policies, but certainly there are policies that we're looking at to kind of address some of those issues.
So the question is, for the chemical neuroscientists, where do you find these miracle berries? And you can buy them online, your major online retailer. If you just look for Miracle Berry, there's different brands of them. I find that they all work fairly well. And here's what I recommend you do. You have a food tripping party. Yeah, you get all your friends over, you dose them with these pills, and then you lay out all of these sour foods. You can try pickles, sour cream, lemons, tomatoes. Guinness beer tastes like a milkshake. It's amazing. Have a great time.
For our environmental scientists, is there any reasonable way to harvest carbon dioxide that's already in the atmosphere? Again, an energetically favorable way to draw CO2 out.
The short answer is no.
Why?
It's a lot of... There are ways, but it takes a lot of energy, so that you would probably be producing more CO2 in the process. The key is really to keep it from getting there in the first place.
Follow-up question. Is there any such thing as clean coal in reality?
Is there any such thing as clean coal?
Is there anything clean coal? There is carbon capture. So what you can do is you can burn fossil fuels like coal or oil, and then capture the CO2 before it goes into the atmosphere, and then pump it down under the earth. It can work, but you have to do more research on it. But that would be a way to do it. You can do it that way.
I'll second this as another climate scientist, but as Ed said, let's not put it up there. Right? Let's do that first. Yeah.
There's a question at the back.
What's your favorite online, I think it's for everybody, what's your favorite online research tool or database these days? All right, Google Scholar!
So my favorite online research tool and database is the protein database that contains all of the three-dimensional structures of all the proteins that have ever been solved. And Dirk Troner, I think he would say would be the Cambridge crystallographic database.
It's been endless hours surfing.
Yeah.
We can 3D print them.
Yeah.
At NYU.
got down here, Dirk and I entertained each other with our discussion about how these structures, how this database of structures can be used as a set of tools for architects at the molecular level. We've got so much information to play with, both with regard to large macromolecules and small molecules, and we can now do such a great job of designing new molecules to solve new tasks, both for materials and for diseases that afflict human patients.
So PubMed for most searches on literature, but ProMedMail, which will tell you everything about epidemics anywhere in the world, whether it's for people, animals, or plants.
Okay, I just have one follow-up question to that question, though. What if people, regular, everyday people, want to access scientific research? What if they want to access the studies and find things themselves? What do they do?
For climate research, Skeptical Science is a great website that really gets into the real science. And it'll point you all into the papers if you want to get that deep.
So Skeptical Science for climate? Anything else? We can post them, yeah. We've got a website. We've got a website thanks to our awesome students and sustainability office and everything. So yes, we will post these. Yeah.
I've got another great suggestion for those of you who want to learn more about science, which is talk to a scientist. Not all of us. Data scientists. Love a scientist. Not all of us are so gregarious, but some of us are. And you should find opportunities just to get us to explain what we do in a very direct way. And we actually really enjoy it. Most of us do anyway.
We probably have time for one last question.
One last
if there's
question.
If there's one at the back.
Is there some? Yeah, come on up. Or just scream it out and I'll repeat it.
Okay, this is a question for the gentleman that we serve about
Will.
emotional development. How did they quantify that data?
How did you quantify the emotional development data for the
Okay, so I just want to be clear that the report that we put together, we didn't actually do any original studies. What we were doing was just doing a literature review. That paper was by a scientist named Lawrence Steinberg and his group, and he has a metric called psychosocial maturity, which is, I think up there I called it emotional development or something, but he calls it psychosocial maturity, and there are a few different things that go into that. And you can just, if you Google psychosocial maturity Steinberg, you'll find all the things that get rolled into that. He's made a whole career out of studying that particular phenomenon. It's interesting.
So, thank you so much, all of you. Again, the fact that we could keep going with the stage is a testament to all your energy. And thank you so much. And thanks again to all the speakers. Let's give a round of applause.
There's no dusty ivory tower here.
Right.
We are doing fun.
Thank you. Let's march. Let's support science and go out and have some fun. Thank you so much.